This video is to walk you through the first problem on the practice test. So the first problem asks about a simple pendulum. If you don't know it by now, you probably should have this kind of memorized, that the frequency of a small oscillation for a simple pendulum is omega equals root g over L. And for this question, that'd be enough. But if you want to show that that's true, you can write the Lagrangian of the system and then find the equation of motion and find what the oscillation frequency is. So to do that, the Lagrangian is the kinetic minus potential energy. Since this is a rotation, the kinetic energy is 1/2 m L squared theta dot squared. And the potential energy is negative mg L cos theta, because the length downward is L cos theta. But the Lagrangian has a negative there as well, so there's kind of a double negative that cancels out to be a plus here. And then if you take the partial of the Lagrangian with respect to theta, you get negative mg L sine theta. Partial of the Lagrangian with respect to theta dot is m L squared theta dot. Take the time derivative of the second part, set it equal to this first part, and you get the theta double dot is negative g over L sine theta. That should look like a familiar formula. For small theta, sine theta equals theta, and you have theta double dot equals negative g over L theta. That's a simple second order differential equation with sines and cosine solutions and a frequency given by the square root of this feedback weight. So omega equals root g over L is the oscillation frequency. For the second part, you need to find the amplitude of the resulting oscillation if a forcing function is added to this. Recall from our text, equation 5.64, that the amplitude squared of a resulting oscillation is equal to the forcing function's amplitude squared divided by these two terms in the denominator, how far you are away from the resonant frequency, plus the damping term here. Now in this question here, there's a little bit of a confusing notation that the push amplitude is A, and we're trying to find the amplitude of the resulting motion, which is also an A. So we need to keep those separate. So let's call the amplitude we want to find as A amp. So A amp squared equals A squared over the difference of the squares of the frequencies, so the resonant frequency, and then the push is at 1.1 times the resonant frequency here. All that squared plus 4 beta squared 1.1 omega naught squared. Beta is the damping coefficient, or not coefficient, but this damping factor, and it's equal to the damping coefficient divided by 2m. So beta equals 2m for any damped system in a second order differential equation, and you can plug those numbers in and you get an expression for the amplitude. Now omega squared is g over L, so plugging those in as well, you can find the amplitude as a function of g and L and the mass and the damping. So it should look about right. So the bigger the push, the more the amplitude is. The bigger the damping, the less the amplitude is. If there's no damping at all, then you'd get this term goes away. So if there's no friction, basically, and you get this g cancels with this g, and the total amplitude of oscillation is proportional to 1 over g, because g is gravity pushing back under force, times how much you push, and the torque, which is this L times how much you push. Okay, so that's it for the first problem. Next video will be for problem 2.